I am very happy to announce the next talk by MCA Prize winner, Professor John Pardon from Princeton University. So despite his young age, John already has a long career with many excellent results in different areas of mathematics, beginning from knot theory to symplectic topology, to theory of group action, and now he'll speak about Pontryagin-Thom for orbifold bordism. So please, John, start your talk.
Thank you very much. It's my pleasure to receive the award and to be able to give this talk. So first, I should share my screen. I want to share this one. Great. I'll make it even bigger. Let's see. Yes, let's. I'll try it this size. Great. So yes, my talk is about a Pontryagin-Thom result for orbifolds. So the Pontryagin-Thom construction is a very classical construction, and what it does is it relates it relates bordism groups, which are a geometric object, to stable homotopy groups, which are, say, they are objects which come purely from the homotopy world, and they're much more amenable to calculation. So, or at least different sorts of calculation than you would could do directly for bordism groups. So let me begin by just reviewing what this classical Pontryagin-Thom construction is, so then we can say what it means to have a Pontryagin-Thom result for orbifolds. So first, let's recall what bordism groups are. So this group omega k is called unoriented bordism. So what it is you take it's the free abelian group generated by closed K. Well, okay, just a set closed K manifolds. So an object, an element of this group is a closed K manifold, but you say two closed K manifolds are the same element of this group if there's a bordism. So if there's some manifold W whose boundary is M disjoint union M prime. So if there exists such a bordism, then M and M prime are the same element of the bordism group. So omega k really is manifolds modulo bordism. And bordism is an equivalence relation because you can glue. So if I have a bordism from M prime to M double prime, then I can just glue these two bordisms along their common boundary M prime to get a bordism from M to M double prime. So this tilde here is an equivalence relation. And this is a group. The group operation is disjoint union. And in this case, everything is its own inverse. So this is unoriented bordism because I didn't say anything about my manifolds carrying an orientation. But if you want to consider a bordism of oriented manifolds, you certainly can, or bordism of other manifolds with other sorts of structures, like a spin structure, or maybe a stable, almost complex structure on the tangent bundle, or a stable framing. So a stable framing, well, okay, a framing would be a trivialization of the tangent bundle. A stable framing is a slightly weaker notion. It's an isomorphism like this. So up to adding the trivial bundle, Tm is identified with a trivial bundle. Okay, so what's the Pontryagin-Thom construction? So let's suppose we take a map from Sn plus k to Sn. And we can think of this as this Sn as Rn modulo infinity. And I want to take a base map. So the base point will be infinity, f of infinity equals infinity. And if you prefer just thinking about maps from Rn to Rn and forgetting about infinity, that just means we have some map from Rn plus k to Rn, which is proper. So the inverse image of a compact set is compact. Okay, so if we have such a map, we can take the inverse image of 0. And well, if we first perturb f so that it's generic, and then this inverse image of 0, it's going to be a submanifold. And what's the dimension? It's n plus k minus n, so that's k. So it's a k-dimensional submanifold. And moreover, it has a stable framing. So there's this exact sequence telling me what the tangent bundle of the 0 set of f is. And this gives you an, we're doing topology, not algebraic geometry, so every short exact sequence of a vector bundle splits just by choosing a Riemannian metric. So this gives you an isomorphism between this plus this and this guy in the middle. So what we conclude is that there's a map which from homotopy classes of maps from Sn plus k to Sn to the bordism group, like this. Okay, so I didn't say it, but I wrote it here. If you have similarly, if you have a one-parameter family of maps F, then you get a bordism between F inverse of 0, F1 inverse of 0, and F2 inverse of 0. And moreover, there's a way of taking a map from Sn plus k to Sn and getting a map from Sn plus 1 plus k to Sn plus 1. Which preserves the 0 set as a framed manifold. So we can add this direct limit here. Okay, so the point here is that this is a geometric bordism theory, and we've related it to something from homotopy theory. So that's one direction, and you can go in the other direction as well. So if I have a closed K manifold with a stable framing, then I can embed it into Rn. So that's this. I just choose any embedding into Rn. And now I want to argue that the image of this embedding is the 0 set of some map F. So to do that, first I should say that okay, what is the derivative of E? That's some map on tangent spaces, and E is an embedding, so it's injective on tangent spaces. So Tm injects into this trivial bundle Rn plus k. Now, stable framing consists of this data. In particular, it's an embedding of Tm into a trivial vector bundle. Now, all such embeddings are the same once you stabilize enough. So if we increase n, right, this is how you show that the Grassmannian, the infinite Grassmannian is the classifying space of classifies vector bundles. You show that every vector bundle has a homotopically unique embedding into a trivial vector bundle. In particular, any two embeddings of your favorite vector bundle into a trivial vector bundle become homotopic once you increase the dimension enough. Great. So now I think it's time for a picture. So we've embedded M into as this this blue curve, E of M, that's the image of our embedding, into Rn plus K. And it has a tubular neighborhood. Now, the tubular neighborhood is the total space of the normal bundle, but the normal bundle is trivialized by the fact that M is framed. The framing was this data. Right here is a trivialization of this quotient. So this normal bundle, this tubular neighborhood, the total space of the normal bundle, this green stuff, is actually just M cross Rn, the trivialization. And so then I can consider the function which just projects onto this Rn factor. And that gives me this map from Rn plus K to Rn. It sends everything outside of this tubular neighborhood is sent to infinity. So then, if we call this map F, then F inverse of 0 is M, and moreover, it's the framing you get from this presentation as the zero set of F is the same as the framing we started with. So so this gives a map in the reverse direction from bordism to some homotopy group. Great. So what I want to describe is how to make this work for orbifolds. Right. Okay. So before we get to that, let me just summarize. So this is the result of Pontryagin-Thom, which is that these maps are inverses to each other. So not only do you have are they related, and in fact it's just the same group. The bordism group is literally isomorphic to this homotopy group on the right-hand side, or more precisely, a direct limit of homotopy groups. So you can put on here on the left-hand side any of these other flavors of bordism that I said at the beginning: unoriented, oriented, almost complex, or whatever you like. So these usually go under the name of a geometric bordism. Theories, geometric in the sense that it's just literally manifolds with modular bordism. And on the right-hand side, there are corresponding other things you can write here, which of course, I mean, the reason I chose to do this example with stably framed bordism on the left-hand side is because the right-hand side is particularly simple in that case. But there are more complicated things you can write on the right-hand side here, which go into the name homotopical bordism. Theories, which also correspond via an isomorphism to the other theories on the left. Right. Okay, so let's do a quick introduction to orbifolds. So what is a manifold? It's some topological space, and it has an atlas of charts by open subsets of Rn. And really, okay, I should say what I'm defining here is a smooth manifold, because I require that the transition maps, meaning you look at the overlaps. Here you go from the inverse image, the overlap in one of the charts to its inverse image in the other chart by going around like this. That should be a diffeomorphism. It should be a smooth manifold. Okay, so the only difference, so that's a smooth manifold. The only difference between a smooth manifold and a smooth orbifold is that with a smooth orbifold, instead, the local models are more general. So the local model is Rn modulo a linear action of a finite group. So here I should say G acts on Rk is a linear action. So i.e. G there's just a homomorphism from G to GLK of R. So there's a subtlety, which is that an orbifold is not merely a topological space. It's a more more complicated sort of object, topological stack, and it's that sense in which you can consider things like transition maps and asking for this to be a diffeomorphism or isomorphism over the overlap. Basically, the point is right. Let me explain why orbifolds are topological stacks, not just topological spaces. So if we take something like R2 and quotient by the action x comma y is equivalent to minus x comma minus y. So that's a z mod 2 action. Then this is homeomorphic to R2. So as topological spaces, these are the same. As orbifolds, they are not the same because an orbifold in some sense remembers the stabilizers. So this orbifold on the left here, as a topological space, it's just R2, but there's a special point at the origin which has, you might say, Z mod 2 isotropy. So in particular, it remembers the fact that the origin was a fixed point of this group action, and the other points were not fixed points. So at any point of an orbifold, you have an isotropy group GP, which is a finite group, and moreover, there's some open neighborhood of P, which is isomorphic as an orbifold to RK modulo GP for some k-dimensional real representation of the finite group GP. Okay. So these finite groups are the main point, the main thing to deal with when you're thinking about orbifolds. Right. So for the Pontryagin-Thom construction, there are really two steps. We went from geometry to homotopy and back. So I guess the first step I want to talk about here is transversality. So that would be going from homotopy to geometry. So let's put ourselves in the following situation. We have an orbifold, and we have a vector bundle over an orbifold. And what I want to convince you of first is that it's no longer the case that you can perturb any section to be transverse to 0. Okay, so first of all, let me explain what exactly we mean by a vector bundle over an orbifold, because well, there are a few different things one could mean by locally trivial. A vector bundle will be locally trivial in a certain sense, but not in the strongest sense you might imagine. So if you have M and E, what you have is there are local charts where this is RK modulo G. Every orbifold is locally of this form. And in such a chart, E is given not by this. So that's wrong what I wrote. That it's too restrictive. It's not that. It's Rn, it's Rk cross Rn modulo G. So here there are two homomorphisms, G to GLK of R and G to GLN of R. So another way of saying that, or maybe a little bit more informally, is that, so if you have your orbifold M and you have some point, then the fiber EP of your vector bundle over P, well, it's a representation of the isotropy group GP. It's not just a vector space. It has this extra structure, and this imposes a lot of rigidity. So for example, let's consider this vector bundle over an orbifold. So I mean, it's literally just this local model that I said everything is locally. So let me upgrade my eraser. Okay, so this this V mod G is my orbifold M, and this is the vector bundle E, or its total space. So we look at a section. So a section has to have a section like this has to vanish at 0, because, well, I'm just going to choose any two representations of G, and I want the second one to have 0 in invariant part. There are no invariant vectors. So that means the value of the section at 0 has to be an invariant vector, and hence it has to be 0. The reason it has to be an invariant vector is just because, I mean, 0 is a fixed point of the action of G on V. And the section well, to give a section like this, to give a section S, it's equivalent to give just an equivariant section a G equivariant section of the situation before U quotient. Yeah. Okay, so its differential at 0 is also G equivariant, and if it were transverse to 0, if the section were transverse, then it would have to be this differential would have to be surjective. But we can certainly find representations which just have no non-trivial homomorphisms between them. For example, G could be Z mod 2, and V could be the trivial one-dimensional representation, and W could be the non-trivial one-dimensional representation. Now that's an ineffective orbifold because the action of G on V is trivial, and some people don't like ineffective orbifolds. So if you are such a person, then you could take G to be Z mod 3, and take V and W to be both, to be distinct non-trivial representations of, say, two-dimensional rotation by 2 pi over 3 and rotation by 4 pi over 3. So then that would also satisfy these conditions. So there are plenty of examples. Almost anything you'll write down will have this problem. Okay, so there's a remarkable result of Wasserman, which is been around for some time, which gives you a sufficient criterion for when when a vector bundle has a section which is transverse to 0. It's not quite if and only if, but it is somehow the correct strength to give us exactly what we need to make Pontryagin-Thom work. So before maybe now is a good time to stop for questions. I think we're about exactly halfway. So people can, I guess people can just unmute themselves if they like to ask.
Okay, I think
John,
you can continue.
May I ask two silly questions? Sorry
Yes.
about that. When you show the definition of the orbifold, you are using two groups. Do you need some compatibility between the groups acting on representations?
Yeah. So so as I said, this object RK, when I write RK mod G, I didn't really say what I mean by that. I mean, somehow, I don't mean the topological space quotient, I mean the topological stack quotient. So that's some sort of object, and whatever it is, it remembers the fixed points, the isotropy groups of each point. And so part of this being a diffeomorphism means that the isotropy identifies isotropy groups, induces isomorphisms on these groups. Now you could certainly have, say, one that doesn't mean, of course, doesn't mean that G and H are the same, because maybe zero has isotropy group G, but maybe that's not an overlap. So they could be different groups, certainly.
Okay.
Probably
and
you can.
Yeah.
I was just going to say, probably you can find an atlas where always, H is a subgroup of G or something, but if you wanted to.
Okay, but you have not so many possibilities, because if they are finite, okay, depending on the others, things like that. And another maybe a stupid question: when you talk about the fiber bundles over the orbifold, you take to the product of two representations.
Yes.
Can be thought algebraically this like the tensor product of two representations and quotient by the action of G?
Oh, it's I guess it would be direct sum, not tensor product. It's a setwise product when I write product.
But you think the action of G to be the diagonal one?
Yes, yes, diagonal, yeah, diagonal action.
Okay. Yeah, thank you.
You can go ahead.
Yes. Right. So what does Wasserman tell us? So Wasserman gives us says exactly what data we need to trivialize this problem that I described right here. So we need the following somewhat complicated operation. So, okay, it's not that complicated. So if you have a representation of a finite group, decomposes into irreducible representations, and we're in characteristic 0 because we're looking at real representations, so this is true. And I want to delete all the copies of the trivial representation. So that's this operation here. So when I write subscript G hat minus 1, that just means you take whatever's in the parentheses and you remove all the copies of the trivial representation of G. Okay, so I can do this to a vector bundle where the group G is the isotropy group. So if I have a vector bundle, the fiber over a given point P is as a representation of GP, and I remove all the copies of the trivial representation from that. So the result is no longer a vector bundle. It's just some sort of, well, it's a vector space for every point, which is a subspace of my vector bundle. So what we need is a linear map from Tm to E, which at every point is not quite surjective. Well, I don't require that it be surjective. I require the weaker property that it's surjective after you forget about all the trivial representations. So this condition, it's a purely sort of Orbi condition. It's only non-trivial at the points where the isotropy group is non-trivial. If M is a manifold, GP is always the trivial group. So all representations of the trivial group are completely trivial. And so this map is simply the zero map. It's the zero map from 0 to 0. And so it's always surjective when GP is trivial. So there's only a non-trivial condition at the points where there's non-trivial isotropy. And it basically says, it gives TPM a fighting chance of surjecting onto EP via sort of the differential of a section. So the conclusion, so that's the hypothesis. The conclusion is that not only do there exist transverse sections, but you can perturb any section to be transverse. And the basic idea of the proof is to use this alpha as a guide for how to perturb your sections. You do some sort of inductive perturbation over the various strata of M. M is stratified by the order of the isotropy group, and you inductively perturb over all the strata. I should say this is somehow a reformulation of Wasserman's result. I think Wasserman basically just stated this for M equal to Rn modulo G. But the proof gives you this more general result. Okay, so let's see. So one thing this tells us is that we get at least a map like this. So if we have an orbifold, and on that orbifold we have an open subset U, and the surjection from that tangent bundle of that open subset U to I guess E should be a vector bundle over U. So maybe I should add that here. E over U, a vector bundle, a surjection from TU to E, and a section of E over U with compact zero locus. So maybe I should just draw this too. There's a lot of data. So here is M. M we regard as fixed. So then what else are we going to? So element on this left-hand side consists of an open set U, a vector bundle E over U, and some section with compact zero locus. I don't know how clear that is. This is S inverse of 0. So it does not approach the boundary of U. And this extra homotopy theoretic piece of data, which I won't try to draw. Okay, and these are considered up to homotopy. So this is a somewhat complicated piece of information, but it's purely it lives in the world of homotopy theory. You can write down some sort of classifying space in some sense, such that this set on the left is simply the homotopy classes of maps from M to that classifying space. So if you think about it, it's you can sort of guess how to write down such a classifying space. Okay, so then there's a map. So Wasserman tells us that there's a map here, because Wasserman tells us that we can, using alpha, we can perturb the section S to be transverse to 0, and we get a closed suborbifold. We make its 0 set transverse. It's a closed suborbifold of M, and it's well defined up to bordism. That uses somehow the relative version of Wasserman's theorem. If we have two sections which are transverse, and the homotopy between them is not transverse, then we apply Wasserman relative boundary. Okay. Yeah, so that's what I wanted to say for this this direction. So now what about the other direction from geometry to homotopy? So how does that work? So remember, what did we do for manifolds? We began with the manifold, and the first step was to embed it into Rn. And to do that, we could just take a generic smooth function. The generic smooth function from a closed manifold to Rn will be an embedding provided n is sufficiently large. Okay, and more precisely, the space of embeddings becomes contractible in the limit as n goes to infinity. So embeddings from M into Rn, we take the direct limit as n goes to infinity, and this is homotopy equivalent to a point. Okay, so why does this work? So why is this true? So it helps to separate out the two key properties of Rn which make this true. So the first is that Rn is contractible. And so what that means is that the space of maps from M to Rn is contractible. That's the space of all maps. And the second key property is that Rn is high dimensional. And this tells us that the locus of maps which are not embeddings has really high codimension. So what that means is taken together, these two things mean that space of embeddings from M to Rn is highly connected. So that's even better than this statement, even stronger. Okay, so if we want to do this for sort of an arbitrary orbifold in place of M, well, we want a sequence of orbifolds which does the same thing. We can't use Rn. So if you embed an orbifold into something, then well, any embedding of orbifolds in particular is injective on isotropy groups. So Rn has trivial isotropy groups. The only thing you can embed into that are manifolds. So you might naively guess, maybe I can embed any orbifold into, say, Rn modulo Sn, the symmetric group, or any other group acting on Rn. Maybe you can always do this. This is a natural first thing to ask. Maybe this is a nice somehow universal sequence of orbifolds which you can embed anything into. But it's easy to see this does not work because here's a covering space, and I can pull it back. If there is such an embedding, I can pull it back to get M tilde, and so then M is equal to M tilde modulo Sn, and M tilde is a manifold, right? Because it's a submanifold of Rn. And there are many orbifolds which are not global quotients by finite groups. You just take the two sphere and have one orbifold point with Z mod 2 isotropy, for example. That's not a global quotient by a finite group. Okay, so the sequence of orbifolds Mn that we were looking for, it's not so explicit. I'll say something about it, but it's somewhat mysterious, at least to me. So first of all, so what replaces this first property, contractibility? It's not contractible. The property you need is that the space of representable maps to Mn is contractible in the limit n goes to infinity. For the purposes of this talk, a representable map of orbifolds is a map such which induces injective maps on isotropic groups. And every embedding is representable. Representable is maybe something. Anyway, so if you're talking about embeddings, all of them have to be representable. Okay, so that replaces this property number one. Property number two is that when you take the tangent bundle to Mn and you look at the fibers, so okay, a fiber over a point with no isotropy is uninteresting. It's just a mi-dimensional vector space. At a point with isotropy group G, you can decompose the tangent space into representations of G. And I want all of the irreducible representations to occur with very high multiplicity. So that's right, a strengthening of this property number two. So not only should we be high dimensional, we need, in fact, all these isotypic pieces to be high dimensional. Great. So property one specifies a unique homotopy type. You can just, some universal property about what maps into it look like. So it's not surprising. It specifies unique homotopy type. So this is, you look at the two category whose objects are finite groups. Morphisms are group homomorphisms, injective group homomorphisms, and two morphisms are conjugations between group embeddings. And you take the nerve. Well, you don't exactly take the nerve, but you take this realization, which is modeled on the nerve, and that's your homotopy type for certain reasons, which I don't want to get into. This space is called R of a point. So it's some infinite dimensional orbicW complex. So if you have any CW complex, you can realize it as a manifold. What do I mean by that? If you have any homotopy type, you can realize it as a manifold. Moreover, you can realize it as a high dimensional manifold just by crossing with Rn. Now, if you have an orbi-homotopy type, meaning you have something of like this, but built out of cells which have this this sort of thing in it, it's not immediately obvious that you can build an orbifold which is homotopy equivalent to it. The key point is the following. To prove that is the following result. So maybe I should define for you an orbispace. So it's like an orbifold, except instead of being locally modeled on Rn modulo a group, it's just modeled on a CW complex modulo a finite group. So a reasonable topological space modulo a finite group. And really the only ones we need to be caring about are glued from orbicW complexes, which are things which are glued up out of things like this: cell, cross, point modulo a group. Okay, so this theorem essentially says that there are enough vector bundles on any such orbispace. So on a compact orbispace, you can find a vector bundle such that at every point, all the isotypic pieces of the representation are non-trivial. That is, okay, said more elementarily, you take EP, every isomorphism class of irreducible representation of GP appears in EP, appears at least once. Yeah, and roughly speaking, these vector bundles, they sort of play the role of trivial vector bundles in algebraic topology. So like I said at the beginning, when you're constructing classifying spaces, you really need classifying space of vector bundles. You really rely crucially on the fact that every vector bundle can be embedded into a trivial vector bundle, and moreover, it's a homotopically unique way of doing that. So if you want to talk about classifying spaces in the orbispace context, this is one fundamental thing you need. Another way of stating this, actually, a corollary, is every compact orbifold M is isomorphic to N modulo G for some compact V group G, acting smoothly on a smooth manifold N with finite stabilizers. So that's another way of saying this. Okay. So using these two ideas, I mean, using these two directions, I said how to go through. In the orbifold context, I said how to go from the homotopical picture, homotopical bordism to geometric bordism, and then just now I said how to go from geometric bordism back to homotopical bordism, or at least I explained the key step. And when you're going from homotopy to geometry, the key step is transversality. And you have to take a section and make it transverse to zero. To go from geometry to homotopy, the key step is embedding. You have to take your orbifold and embed it into something. And that's what we needed here. So when you combine all of these in the relevant way, you get a Pontryagin-Thom isomorphism for orbifolds. So I'll just sort of explain informally what the key players are. So Mn, this is the sequence of orbifolds from before. You compact orbifolds with boundary, and you take this Mn relative its boundary, desuspended by its tangent bundle. So that makes sense in a certain category of orbispectra. And then you apply this, there's a certain cohomology theory on orbispectra introduced by Stefan Schwede under the name homotopical bordism. And then the theorem is that this direct limit on the left is indeed closed K orbifolds modulo bordism. Now, this left-hand side looks a little bit strange, but there's a very intrinsic operation on orbispectra. There's a contravariant involution called the D, which generalizes Spanier-Whitehead duality, and that really is what's going on with this rel boundary and desuspension. So the interesting thing here is that, well, even for the regular Pontryagin-Thom isomorphism, homotopical bordism theories are, well, they're really homotopical cobordism theories. They're most naturally cohomology theories. Whereas bordism theories, geometric bordism theories, are more naturally homology theories. And this means that you're basically any sort of isomorphism between them essentially has to involve some sort of duality to go from a homology theory to a cohomology theory. Anyway, that becomes more apparent in this Orbi setting. So I think I'm at the end of my allotted time. So I'll ask again for questions.
Okay, thank you, John. So may I ask you something? So can you use it for some computations, this isomorphism?
Yes, let's see. So this R of a point is this sort of rather complicated space up here. And anytime you have a filtration of this space, you can filter it in many, many ways. You could filter by the order of the group, or by P, or then you get a spectral sequence for this with something. You don't. On the other hand, though, you don't really need the full force of this result to say that. I mean, you can just say you take. I mean, you can take orbifold bordism. You could sort of take bordism of orbifolds. Okay, so every orbifold has a homotopically unique representable map to this, but you could also consider orbifolds with a representable map to whatever complex you want, just using the fact that it's a homology theory is going to give you the spectral sequence. So that's not really a true application.
But you know, historically, like Pontryagin invented this kind of construction for computing homotopy group of spheres.
Yes.
So maybe you can. So can you then compute left-hand side and say something about it?
I have not thought much about this. I think orbifold bordism groups are maybe known only a little bit up, some in dimension 3, and that's, I mean, up to dimension 3, and that's it. But one needs to do more calculations here. I mean, there are these two flavors of bordism, or orbifold bordism now. There's ordinary bordism and then derived bordism, which can be non-zero and negative degrees, negative dimensional degrees.
Any other questions?